Alright, so in this second part of the video for section 3.3, we will discuss how to solve related rates word problems using implicit differentiation. Alright, so we have a couple of problems here, but before just going directly to the problems, I would like to explain what's really the, the, the idea of what we are trying to solve. For example, so usually we have a function y equals and let me just call it y equals some f of, well, not f of x, let me just call it y equals x. Well, whenever we take a derivative, now take the derivative of y, that is y prime, that'll be the derivative of x, which is 1. All right. Now, when it comes to related rates, another way to describe related rates is to introduce rates of change. In this case, rates of change. With respect time. So we are going to introduce pretty much a third-party variable here. That is going to be t. So notice in this case, we have y equals to x. So, well, this simple function y equals to x relates the inputs, relates the inputs x to the outputs y. Well, now in this case, when it comes to finding the derivative of this, well, the derivative is 1. All those points lie on a line whose slope equals 1. But well, when we do the related rate, we are going to look at this function in a slightly different way. So we are, again, like I mentioned before, we are going to introduce some sort of a third-party variable, that is y depending on time t and x also depending on time t. So when we find these derivatives, we are no longer differentiating these functions with respect x, but rather with respect time. For example, dy instead of dx, that's going to be dx. And then over here, we are taking the derivative of x, which is 1. Yes, that is still true. However, this x is also depending on another variable, which is t. So essentially we're doing a chain rule in combination with an explicit differentiation of the x dt. All right, so as another example, for let's say y equals x cubed, so that's another example, the derivative of y, which is, well, number 1, let's introduce this variable right here, equals x, which depends on t, but this is cubed. So we take the derivative of y, which is dy, but no longer with respect x, but rather with respect time. Okay, and then let's do 3 times x of t to the second times the derivative of x with respect time, that is dx with respect t. Well, right now with just symbols, with just algebraic functions may not make too much sense for now. However, if we if we apply this to situations like in geometry or in science like natural sciences, economics, many other applications, we can find rates of change at a particular point when a system is in constant change. You know, for example, let me give you a very simple system right here. Okay, so suppose we have um, suppose we pour, I don't know, we pour liquid on a flat surface. So as we, let's see, let's pour water. Okay, so we're gonna pour water here on a flat surface. And well, as water gets on the surface, typically when we pour water on a surface, it starts growing in circles. So gets a circle, and this circle gets bigger the more water that we add on that flat surface. So in other words, that amount that circular for that circular shape of water becomes bigger and bigger. The radius gets bigger, so the area also changes. It also gets bigger. Or if we leave that water, with time it starts to disappear. Well, it actually boils, the water boils, and that circle of water gets smaller and smaller, so in other words, the area changes, the area gets smaller because its radius also gets smaller. So let's recall the formula for finding the area of a circle. Well, area equals pi r squared. So in this case, in this situation, we are going to introduce this third-party variable, time. So this time, both the area of that circular shape due to pouring the water changes with respect to time, because the radius also changes with respect to time. That is, dA with respect t equals pi, okay, so 2 times pi r of t, 2 minus 1 is 1, times the derivative with respect t. So let's see. In this case, we have found an expression that describes the change of the area with respect to time due to a change in the radius. Okay, let me repeat that. We're finding an expression that describes the change in the area of the circle due to a change in the radius, all right? So, and well, this value could be positive or negative depending whether this water, we're pouring more water, or that's a positive case, or the negative case if we leave that circle of water to let it dry, which time gets smaller and smaller all the time. Well, of course, typically that's not like perfectly circular. So in this case, in this case, we assume that this is perfectly circular. Of course, we don't have to use the t right here anymore. I mean, I'm talking about this one. So we can simply, so when it comes to area equals pi r squared, if we want to describe the related rates, which that is the changes with respect to time, we can simply dA dt equals 2 pi r squared dr dt. All right. Another situation, well, suppose that how about we have this water instead? Well, maybe not water, maybe just having this rectangular surface for which we have a length and we have a width. And we are going to relate the area of this rectangle, which is length times width. So area equals L times W. All right, so again, this area will change with respect to time. So the length will change with respect to time, along with the width to change with respect to time. So, well, so for example, think of an animation here, in which there's 4 possible scenarios here. Number 1, both L and W get bigger and bigger with respect to time. Or second scenario, both length and width get smaller with respect to time. Third case scenario, length gets bigger, however width gets smaller. Or the fourth case scenario, the width gets larger, but the length gets smaller. Okay, so four case scenarios, and we describe this with derivatives, but this time with respect to time. So when it comes to taking the derivative, it is the total area changing because of time. That is, well, in this case, we're going to use the quotient, the product rule. So the derivative of L, which will be dl with respect time, times the width plus the derivative of the width with respect to time times the length. All right, and this is how we describe this change of the area by modifying the parameters length and width. And again, if we could have both both of these rates to be negative, both positive, one negative, one positive, or another one positive, one negative. Okay, so I think after this we're ready to look at what's going on with the examples that we have. Okay, so this is a very typical, very classical example to introduce relates. So suppose that a spherical balloon is inflated by a continuous flow of air from an air compressor at a rate of 2 inches cubed. Here I meant cubed, but the PDF will be updated. 2 inches cubed per second. All right. How fast is the radius of the balloon growing when the radius is 3 inches? So of course, they will give us a piece of information. You want to know how fast is the radius changing at the moment when the balloon has a radius of 3 inches. And well, in this case, there could be two possible scenarios. Either the balloon getting inflated, which is our case, or the balloon getting deflated, and that'll involve a negative rate of change. So let's start with using the formula for the volume of a sphere. So let's see. For formula, the volume of a sphere, volume V equals 4/3 pi r cubed. All right, 4/3 pi r cubed. That's the volume of the sphere. Of course, this is what's going on in the background. So recall that these two variables here, both the volume changes with respect time, pi is a constant, and the radius also changes with respect time. Okay. That just wanted to write this down just so we don't forget that these two variables are changing with respect to time. So we're going to take the derivative of this volume, so that is dv, but in this case with respect to time. That's going to be 3 times 4/3 pi. The derivative of r cubed with respect to time, well, number one is this 3 times r squared times dr dt. All right, and of course you might want to cancel these two degrees, and dv dt equals 4 pi r squared dr dt. Okay, now what kind of information are we given and what are being asked to find? Well, on the one hand, they're giving us a rate of change because of the units. Okay, so we have a rate of 2 inches per second, inches cubed rather. This should have been 2 inches cubed per second. Okay, these inches cubed per second are represented by the change in the volume. So at this point, what you might want to do is put units to every single derivative here. That is dv dt, that is inches cubed over second. That's what our dv dt is. Radius is inches and dr dt is inches per second. Now, what are we given? What are they asking us for? So on the one hand, they're giving us dv/dt. They are also asking us to find how fast is the radius changing at the moment when the radius is 3 inches, right? So our unknown will be how fast is the radius of the balloon growing. So this is our question. So we know, we know, we don't know. So let's solve for the RDT, and we do that by simply dividing both sides of this equation by 4 pi r squared. So let's divide both sides by 4 pi r squared, and that's going to leave us with dr dt, which is the rate of change of the radius with respect to time. That is how fast the radius of the balloon is, in this case growing, because the balloon is being inflated. That is equals to 1 over, that's a 4 pi r squared dv dt. And all we have to do here is simply plug in the numbers. So dr dt equals to 4 pi r squared, that is r squared, which in this case is, well, actually, let's put unit. It would be great to put units just so you can see how that works out. So the radius, which is 3 inches, that quantity gets squared, times the rate of change of the volume, which in this case is this quantity highlighted in blue, that is 2 inches cubed over per second, rather, not over second, per second. Okay, so doing the numerical calculations here, well, this is going to lead us to, well, 3 squared, that's going to be 9. 9 times 4 pi, that's going to give us 36. Well, let me just, yeah, 36 in the denominator. So dr dt, that's 36 pi inches squared in the denominator, and 2 inches cubed per second. Notice here 2 things will happen. Number 1, the 2 goes away, leaving us with an 18, and inches squared cancel with inches cubed to leave us simply inches to the first, which is just inches. Now that's gonna be dr dt, and that's 1 over 18 pi inches per second. And the units check over here because inches are units of radius or length, as just like inches cubed are units of volume. Okay, and of course typically our homework might want some answers to reduce to, or rather approximated to certain decimals. This in decimals will be, or approximately rather, 0.018 inches per second. All right, and this was our first example in related rates. Let's look at a second example. On our second example, an airplane is flying in a circular holding pattern with a radius of 2 miles, well, a radius of 2 miles away from an airport, right? And the path of the plane can be described by the equation x squared plus y squared equals to 4. When the plane is at the point x equals the square root of 3 and y equals 1 mile, so the airplane is at this position, they're giving us one piece of information. As showing in the figure here, it is traveling north at 300 miles per hour. This is a little bit tricky to interpret. It is traveling north. Okay, So in this case, notice these two arrows right here are telling us two different pieces of information. Number one, the component, the horizontal component of the velocity of the airplane and the vertical component of the velocity. So because in this case, they're telling us that it is traveling towards the north at 300 miles per hour. Because it's towards the north, that's the vertical component of the velocity of the plane. In other words, it's going to go on the y component. This is going to give us the following: the dy dt, that is the change in the vertical distance, that is 300 miles per hour. Instead of writing mph, I'm going to write it this way, mih, because we might need this later. Let me see, let me check my notes. No, that's fine. We won't have to. Let me just go back to mph. mph is fine. Well, this is dy dt when x equals the square root of 3 and y equals to 1. Okay, so that is the pieces of information that we are giving. The question is, how fast is it traveling west? So at this point, okay, let's describe what's going on. At this point where the x equals root of 3 and y equals to 1, look at the direction of the airplane. So it's traveling north, both to the north and to the west. So in other words, they're asking us the x component of the velocity, or the horizontal component of the velocity. In other words, they're asking us for the x dt, which is our question here. So let's get started and write this x squared plus y squared equals to 4. Okay, so because this is with respect to time, recall that this x changes with respect to time and y also changes with respect to time. All right, so the derivative here of x squared is 2x dx dt plus 2y dy dt. And the derivative of 4 equals to 0. Okay, well, what kind of information do we have over here? Well, so let's see. In this case, we know dy dt, that's the speed of the plane towards the north, the dy dt. We know a value for y, we know a value for x, but the one that we don't know is the dx dt. We don't know that one. That's actually the question. So let's just plug in values over here and let's see. So 2 times the value of x, which is square root of 3 miles, let's put the units, dx dt, which we don't know, plus 2y, where y equals to 1 mile, and times dy dt, which is 300 miles per hour, and that equals to 0. So let's simplify all this. So 2 times 1 times 300, that's what is this going to be? Well, so that's 600, and I'm going to leave the units miles times miles per hour. Some units are going to cancel, you'll see how, and don't forget about this dx dt times 2 square root of 3 miles. Okay, so, well, then that equals to 0. So this will be the following. No, so that is, let me subtract the 600 to the right hand side, 2 root of 3 miles dx dt equals negative 600 miles per hour. And dividing both sides by 2 root of 3 miles will lead us to get dx dt. So 2 root of 3 miles, 2 root of 3 miles. Now see what's going on, just so you can, I'm leaving the units just so you can see the consistency with all of them. Okay, so cancel all this as well. Dx dt, and that's a 600 over 2, that's a 300, and actually negative 300 over the square root of 3 miles per hour. And well, you might want to rationalize this number. So that's because of course you might recall that we don't like radicals in the denominator. That will be okay. That's dx dt negative 300 root of 3 over square root of 3 times itself, which is 3 miles per hour, which is negative 100 root of 3 miles per hour. And well, simplifying to an approximate answer to one decimal place, this is approximately not equal, it's actually just approximately 100 negative 173.2 miles per hour. Well, and you might wonder, why is this value negative? Well, a negative velocity, a negative rate of change in motion looks like slowing down, and well, if that might make us think, well, that doesn't make sense, because if the airplane is in holding pattern, well, looks like it might be like a constant velocity. It's not slowing down, and now look at that slowing down velocity. That's kind of fast to go, like to like step on the brake like that steep, you know. The thing is, the negative here is the negative here, it's because of the direction towards the west, you know. Otherwise, if it went towards the east, well, the direction is to the positive x-axis. So that's why in this case is it's negative. Okay. And let's do one third example. So we have two cars, A and B, and they're traveling toward the same intersection. And well, the thing here is that none of these cars are planning to stop. Car A is 0.5 miles from the intersection, moving towards the east at 40 miles per hour. Okay, let's label that. So 40 miles per hour. While the other car, car B, which is moving to the south at 60 miles per hour. That is this one right here. Okay, so the question here is, how fast is the distance between the two cars changing? Well, what about that distance? Well, it's a little bit hard to see the picture here, especially because it's in perspective. So I'm gonna draw a different picture. So is this triangle right here? Okay, so in this case, this one is going towards the east, and this car is going towards the south. Okay, well, there is a distance in between the two cars that we will call S. Okay, that's the distance here. And well, the exact moment where this car is, let's call this, well, for whatever reason they call X and Y. I know this is weird. So X equals that's 0.75. That is car B, 0.75 miles. It's 0.75 miles from the intersection with a speed of 60 miles per hour. That is the dx with respect t is 60 miles per hour. Okay. On the other hand, for the car that is going towards the east, that is car A, uh, we have a y value. I know that's weird. That's what the picture has here, y and x in the reverse order. Y, which is 0.5, and the dt of 40 miles per hour. All right. Now, the closer these two cars get, number one, this distance will get smaller, that distance will get smaller, and so this distance, the distance s, will get as well smaller. In other words, it's going to shrink as well. Now, the information for s, um, well, there's also a change in the distance s with respect to time that actually we don't know what it is. Now, let's set up the formula or the mathematical model that describes this situation right here. Notice, in this case, the picture that this gives rise to is that of a right triangle along with the lengths of the sides. So, what mathematical model do you think it will relate this? Well, you guessed it right. It's the Pythagorean theorem. And in this case, the Pythagorean theorem that tells us c squared equals a squared plus b squared. But of course, relating it to our terms right here, c squared, the c which is the hypotenuse, that let's call it, that's going to be the s, and a which is typically the horizontal component, and b which is the vertical component, that is y squared plus x squared. Okay, so let's go ahead and do the calculus for this expression, for this mathematical model that is the Pythagorean theorem. Okay, again, let's recall that we mentioned that both x, y cancel, and so does the hypotenuse. All the lengths of the triangle here change. Okay, so in the background, this is what we have. We have some s depending on time squared. We have y depending on time on the background. And we have x depending on time in the background. Of course, you don't have to write all this. I'm writing it in a different color in orange just to have that as a reminder that when we take these derivatives, we are supposed to differentiate this with respect to x. Okay, I'm going to leave it here and I'm going to take the derivative. So the derivative of s squared is 2s times ds dt equals 2y dy dt plus x 2x dx dt. Okay, so it would be a good idea to simplify this equation to lowest terms, and we can divide both or multiply both sides by a half. Everything is divisible by 2. That is s ds dt equals y dy dt plus x dx dt. All right, let's see. This is the model that ultimately we will work with. Right now, what do we have? What are they asking us for? Okay, on the one hand, we know the y position, that is the one of the car that goes towards the east, labeled with a y, and its speed. We also know the position x of the car B coming from the north to the south, and we know its speed. And well, they're asking us how fast is the distance between the two cars changing. Well, which distance are we talking about? this diagonal distance in between, which is this one right there. Well, so essentially, they're asking us for ds dt. However, there's another piece of information that we don't have, that is s. Okay, even though we don't have, they're not giving us that piece of information, we have enough information to compute it and then be able to solve this problem. All right, so number one, it would be a good idea to solve for ds dt. That is by dividing both sides by s, and then that's going to leave us with ds dt equals y dy dt plus x dx dt divided by s. Well, we still need to find s. So we are going to find the value of s at a moment where y equals 0.5 and x equals 0.75. We need to find that value of x. So we're going to use the Pythagorean theorem adapted to our situation right here. This one. So let me use a different color here instead. So that is s squared equals y squared plus x squared. Well, so let's see, s squared, which is unknown. We don't know what s is. So we're going to leave it just like s squared equals y squared, which is 0.5 quantity squared, plus x squared, which is 0.75 squared. So I'm going to solve for s by taking the square root of this quantity. 0.5 squared plus 0.75 squared. And using a calculator, this should give us, well, inside approximately 0.8125. And the square root of that number will be approximately 0.9. Okay, so now that we have that piece of information, s at the moment when y equals 0.5 and x equals 0.75, well, we may go back and compute ds dt for our values here. So ds over dt equals y, and in this case y equals 0.5 times the quantity dy dt, which in this case is well, actually, you know what, let me add the units. I was almost forgetting the units, so these are units of distance, so 0.5 miles times dy dt, which is the rate of change, which is 40 miles per hour, plus x, which in this case is 0.75 miles, times the velocity for that car, which in this case is 60 miles per hour. However, be careful here. I'm going to call it negative 60 miles per hour. Here, the signs and the direction matter. So notice, going back to this triangle right here, notice how, because this is going into the positive x direction, this one is going into the negative y direction. Because it's going down, it's going to the south, this one is going to be negative as opposed to positive for the one that is going west. Of course, we could have had the scenario in which, well, the two cars leave an intersection. So one car leaves the intersection towards the north, one car goes the other car goes to the east. In both cases, they're both positive. Or we could have had the situation in which one car goes to the north with a positive velocity, because just for reference, the one going to the west with negative sign. So here signs matter, and you will see why. I will show you in a minute why these signs will matter in the end. Well, let's keep computing this. Let's divide the whole thing by the 0.9 miles. Okay, so let's over here multiply all this. So after doing this calculation, 0.5 times 40, okay, 0.5 times 40 plus 0.75 times negative 60 divided by 0.9 in our calculator, you should get the following. You should get ds dt equals negative 72 miles times miles per hour. And then notice we have these miles in the denominator, these miles from the numerator, the miles from the denominator, and those miles cancel. And ultimately, the units, it's actually number one, negative 72.2. Ultimately, our final answer, ds dt, equals negative 72.2 miles per hour, which can be rewritten as miles per hour, which are consistent with the units of our derivative ds, a change in the distance, miles, with respect a change in the time t, right? Hours, rather, not t, just hours. All right. And well, these were a few examples on how to solve related rate problems. Well, so number one, so what you have to do here is to identify what mathematical model is the one that best fits for the situation. Like in this case, it was a triangle situation. Now, again, coming back to this negative before I forget, this negative right here, in the end, had an influence on getting this negative final answer, and why our final answer ultimately is negative. And the reason for that is because the closer these two cars get, so this distance can get smaller, that distance gets smaller, this distance in between the two cars, the diagonal distance in between, also gets smaller. And the way to describe that, the distance gets smaller with respect to time, is with a negative sign. All right. And this is the end. Oh, let me, for calling it a day for this video. So this is the end of this video, and as well, and so it is for this section. I'll see you in the next section.